In section 4.5, we're going to look at what are called the rules of differentiation. In 4.3 and 4.4, we learned this idea of what was called a derivative of a function. And the derivative of a function, if you recall, was a limit of indeterminate form. So what I've done here, just as a bit of a review, is I've written down the formula for the derivative of a function. F prime of x equals the limit as h goes to 0, and then we have our quotient f at x plus h minus f at x all over h. This is called the derivative, and what we're going to start looking at now is more efficient ways of finding derivatives. These techniques are called the rules of differentiation. So to begin with, I've started with a very simple function, f of x equals x squared. Now if we wanted to find the derivative, if the question said differentiate this function, what we would do is we would write f prime of x. That indicates that we want to take the derivative. And then using our definition, we would say that it's the limit as h approaches 0. And then you plug x plus h into your function. So we would get x plus h all squared minus the function, which is x squared over h. Now recall, this is a limit of indeterminate form. If you tried to plug 0 in here for h right now, you would not get an answer. You would get 0 over 0. So we have to apply one of our strategies for finding limits, and in this case it's a simplifying strategy. So what we would do is we would expand x squared plus 2xh plus h squared minus x squared all over h. The x squareds would cancel because we just subtract them. We would take out our common factor of h, and we would get h times 2x plus h all over h. Divide out the h's, and now we're free to take the limit. So when we take the limit, the h becomes 0, and we get what's called the derivative, and the derivative would be 2x. We saw this question in the previous section. That 2x represents the slope of the tangent line to this graph at any point. Now, we found the derivative using the definition being what I have written up here. But what I want to show you now is this definition is going to get quite awkward if we start getting into more complicated questions. What if the question had been f of x equals, let's say, x to the 20th? Well, you can imagine trying to find the derivative of x to the 20th using this definition. At some point, you'd have to go x plus h to the 20th, and expanding that would be quite challenging. We'd end up with 21 terms, and obviously we don't want to do that. Or what if the function had been, something like f of x equals 3x squared plus 5x all to the 7th times 2x minus x cubed all to the 5th. The point I'm trying to make is, in calculus, we're always trying to find the derivative of a function. This is called differentiation. But you can see that very quickly, the definition that we've developed is going to become too difficult to use. It's fine for simple polynomials like x squared, x cubed. But the moment you run into a function of this complexity, then using the definition just isn't going to apply. So what we're going to do is we're going to develop the rules. And there's a number of rules in Chapter 4 that we're going to work through. And in this first section, 4.5, we're going to start with the most basic, what are called the elementary differentiation rules. So the first rule we're going to look at, and all of these elementary rules are quite simple. The first rule, so this is our first rule of differentiation, is called the constant rule. The constant rule says that if you have a function f of x, and that function is equal to just a constant, like f of x equals 3 or f of x equals 5, if there's no variable involved, if you just have f of x equals some constant c, okay, so f of x equals c, where c is a constant, then the derivative f prime is equal to, now, what does f of x equals c look like? You may recall that f of x is just a replacement for y. So if you have y equals 3 or y equals 4 or y equals 5, those are just horizontal lines. A horizontal line like y equals 3 would just be a function that looks like this. Now remember that a derivative is just slope of the tangent. Well, if you picked a point anywhere on this graph and you drew a tangent, the tangent would lie flat right on top of the graph. It would be horizontal. Horizontal lines have a slope of 0. So all this first rule says is that if you want to take the derivative of a function and the function is just a constant c, then the derivative is just 0. Now the actual proof of this rule would come from using the definition of a derivative up here. You're not responsible for knowing how to prove these rules. I don't think that's really important. What's important is that you learn the rules themselves and how to apply them. So I'm not going to actually prove these for you. The proofs are in your textbook if you're interested. They're not very difficult, but I'm not going to bother showing them to you because you're not responsible for it. So there's our first rule. The first rule says that if you have a function f of x equals c, then its derivative f prime of x is just equal to 0. Our next rule of differentiation is called the power rule. It's arguably the most important rule you're going to learn because of the usefulness of it and how simple it is. The power rule says that if you have a function f of x, and that function is equal to x to some exponent n, in other words, a power, then the derivative f prime of x is equal to, now all you do for the power rule is you just take the exponent n and you multiply it out front. So you go n times x, and then you subtract 1 from the exponent. So the derivative would just be n times x to the n minus 1. Now you saw this just a moment ago. For example, if you had f of x equals x squared. You may recall that we just did that question a moment ago, and it turned out that the derivative f prime was 2x. Now notice that it wasn't that difficult to get that using the definition because it wasn't a very hard question, but look how easy the power rule is. The power rule says take your exponent, in this case 2, multiply it out front, so 2 times x, and subtract 1 from the exponent. Well, if you subtract 1 from 2, you just get 2x to the power of 1. It's that simple. So now it doesn't matter how complicated the question is. If you had y equals x to the 10, using the definition of a derivative would be very difficult for this question. But using the power rule just says that the derivative, dy dx, you notice this time I'm using a different notation, dy dx, because of the y equals. According to the power rule, all you do is multiply the 10 out front and subtract 1 from the exponent. And there you have it. That's your second rule of differentiation, called the power rule. And what you'll notice about the rules of calculus is that they're very simple. The rules themselves are not very complicated. These rules apply, this power rule applies for any exponent. So if you had something like y equals the 5th root of x. Now on the surface that doesn't look like a power, but you may recall from Math A30 that when you have an exponent, a radical sign with an index of 5, that becomes an exponent of 1/5. So this is really y equals x to the 1/5. Now we clearly have a power, so the derivative, dy dx, would equal, according to the power rule, we would multiply the 1/5 out front, subtract 1 from the exponent. If you subtract 1 from 1/5, we need to change the 1 to 5/5, so this would become minus 4/5. Now you can leave your answer like that. Some people would rather you take the negative exponent and move it to the bottom, so you could write your answer as 1 over 5x to the 4/5. You even could put the answer back in radical form. The 4/5 would just become 1 over 5, and then you'd have the 5th root of x to the 4th. All of these, we'll talk about this later, but all of these are acceptable ways of writing the answer. The most important thing right now is that you just learn the power rule. And the power rule says multiply the exponent out front, subtract 1 from the exponent. The next rule is called the constant multiple rule. Now, the constant multiple rule, again, like all the rules of calculus, is quite simple. But the important thing here is not to confuse it with the first rule we learned, which is the constant rule. The constant rule says that the derivative of a constant is 0. This is saying, what if you had a function f of x, and f of x was just equal to some constant c times another function g of x. So f of x is equal to c times g of x. Then this rule says that the derivative, f prime, is just equal to the constant c times the derivative of whatever g was, g prime. Notice that the constant does not become 0. It's really important that you don't confuse this rule with the constant rule. This is a constant times a function. So for example, if I gave you the function f of x equals 6x to the 3. So what we have here is obviously a power, but it's not just a straight power. It's a power being multiplied by some number 6, that 6 being a constant. Well, according to this rule, what you would do if you wanted to find the derivative is you would just leave the 6 alone, just leave the constant alone, and then you'd multiply that by the derivative of whatever g is. In this case, g is the x cubed. The original function f isn't just x cubed, it's 6x cubed. So g itself is just the x cubed. Now x cubed is just a power, so the derivative would be 3x squared. And there's your derivative. Now you'll notice that you can put those numbers together, and you'll just end up with 18x squared. So some of you might be thinking, well, why not at the beginning? Why not just multiply the 3 times the 6? Why treat it as a separate situation? And that's a good point. If you have a very simple question like this, where you just have a number being multiplied by a power, we're not actually going to do the question this way. We're going to just go 3 times 6 subtract 1. But in more complicated questions, it's important that you differentiate between a constant and a variable. So since we can take that shortcut, we have one final rule here and that's the extended power rule. And the extended power rule is just the power rule that we learned at the top there, combined with this rule. So it says if you have a function f of x that's equal to some constant c times x to the n, then the derivative, f prime, instead of doing this separately as a constant times a function, this extended power rule says that you can just multiply the power out front. So we would just go n times c times x to the n minus 1. So for example, if you had y equals 4x to the 6th, there's no need to separate this into 4 times x to the 6th. The extended power rule says that your derivative dy dx is just 6 times 4, which is 24, subtract 1 from the exponent, 24x to the 5th. So our last rule for this section is called the sum and difference rule. And the sum and difference rule will help us deal with functions that are made up of functions being added or subtracted together. So this rule says that if you have a function f of x, and that function is just a function, we'll call it p, plus a function q, plus a function r, and then it could keep going for as many functions as we wanted, that the derivative, f prime, is just the derivative of each individual function. P prime of x plus q prime of x plus r prime of x plus, and again we could keep going. Now it seems like these are a lot of rules. I mean, I just showed you 4 or 5 rules, but putting them all together, we can show this in one example. If I gave you y equals x to the fifth plus 3x squared minus 5x plus 2. Now again, I want to remind you that every time we take a derivative, we're actually doing the limit concept. If we were to do this question one section ago, we would have to go the derivative equals, the limit as h goes to 0, and then go through that whole quotient of f at x plus h minus f at x all over h. What I've tried to show you in this section is taking a derivative of a function like this can be very simple with just some very basic rules. So to take the derivative of this, we would just go dy dx equals. Now the first thing we come across is just a power, x to the 5, so that would be 5x to the 4th. Now there's a plus sign which separates these two terms, and according to this rule, if you have a function separated by a plus sign and another function, you just take their individual derivatives. So now we would take the derivative of 3x squared. Well, that's our extended power rule. We have a constant times a power, so that would just be 2 times 3, which is 6. Subtract 1 from the exponent, we just have x. A minus sign is the same as a plus sign. You're just adding an opposite. So the minus sign tells us that we are now leaving a function and moving on to another function. So we would just take the derivative of minus 5x. Now minus 5x is like having minus 5x to the 1. So this is again our extended power rule. 1 times 5, so we're just going to have minus 5. Subtract 1 from the exponent. Now when you subtract 1 from 1, you get 0. X to the 0 is just 1. So in other words, there would be no x. The derivative would just be minus 5. And then plus the derivative of 2. Well, 2 is a constant. It's different than this 5 here. This is a constant times a function. This is just a constant 2, so the derivative would be 0. And so that would be the derivative of our function. You can see how easy that is. We can now differentiate polynomial functions quite simply using these rules. Now just a couple more examples. If you had something like 3 over x minus 5 square root x. I wanted to show you this example just because it looks a little more challenging than the previous one, but the key is just to change it to powers. This is really the same thing as 3x to the minus 1 minus 5x to the 1/2. To do this, you have to know a few laws of exponents, the negative exponent, the fractional exponents. Once you've got everything as a power, this question is no different than the previous one, except your exponents are negative numbers and fractions. So the derivative, dy dx, this is our extended power rule. This would be minus 3. Subtract 1 from the exponent would give us minus 3x to the minus 2. This would be minus. Now we have a separate function. This is our sum and difference rule and our extended power rule. You'll notice that you're using all these rules all the time, but after a while they just become habit. You don't start thinking them as being separate rules. This would be minus 5/2, 1/2 times 5. Subtract 1 from the exponent. And personally, I would just leave the answer like that. Obviously, you could do some simplifying. You could move the negative exponents to the bottom and so on. For now, just leave your answer in that form. The last example I wanted to do was just to make sure you don't confuse, don't try doing something that you can't do yet. This question right here, f of x equals x plus 4 times 2x minus 5. Being that you're just learning these rules, there's a temptation to want to take this rule you just learned here and apply it where it doesn't really apply. This is not a sum and difference rule. This is a function times a function. I wanted to make sure you understood that you can't just take the derivative of each of these terms right here. You could if there was a plus sign in between where this bracket is. If these were just 4 terms being added, it would be your sum and difference rule. But in this case, it's a function times a function. We're going to learn in the next section that we do have a rule for that. But right now, the only thing you can take the derivative of are functions that are being added and subtracted. So what you'd have to do here is before you take the derivative, just do some basic algebra and just expand it. X times 2x is 2x squared, minus 5x plus 8x is plus 3x minus 20. Once you've got it in this form, now it's just the rules that you just learned. So this would just be 4x plus 3. Okay, and that's the end of section 4.5. where we introduced you to the basic rules of differentiation.